Alright, let's start section 1.6. This section is alternating series. So the definition of alternating series is the series is of the form of the mixed sign. So you can see the example here that we have the plus sign and minus sign and minus sign and plus sign and plus sign and minus sign and minus sign and plus sign and so on. So you can see that if you have a series with the mixed sign, so this thing is called the alternating series. And to check the convergence of alternating series, we're gonna learn one technique on this section. So let's look at the statement that we're gonna learn in this section. So for alternating series test, we can check that it is convergent if we check these two conditions. So the alternating series of the form -1 to the n plus 1 times an. So the -1 to the n plus 1 here, this is going to be the thing that gonna swap the sign between plus and minus. So this is the key for swapping the sign, right? This thing gonna be convergent, the whole thing, summation of -1 to the n plus 1 an gonna be convergent if you can check two conditions. So condition number 1 is the term of the series are not increasing in magnitude, or in other words, you can just check that this thing is decreasing. That is enough. And then the second condition, you need to check that limit of n is equal to 0. Well, if you have these two things together, so then you can conclude that the alternating series is convergent. So let's look at example. Alright, so example 21. So we want you to use the alternating series test to check if the series is convergent or divergent. So let's look at part A. So we have -1 to the n plus 1 over n. So here we have a sub n equal to 1 over n, right? Because this is of the form summation of -1 to the n plus 1 times an. So you can see clearly that your an is just 1 over n. So once you have your an equal to 1 over n, you check two conditions. So condition number 1. So is an decreasing? Well, to check that f is decreasing, we can use calculus 1, right? In calculus 1, we learned that if the derivative of f is less than 0, then we can conclude that function f is decreasing. So we're gonna define fx to be 1 over x, and then after that I differentiate f one time, so I have -1 over x squared. So this thing is less than 0. It's mean, yeah, an is decreasing. Alright, condition number 1, check. Condition number 2, you need to show that limit is equal to 0. So limit of an when n go to infinity. So this is limit of 1 over n, right? An is just 1 over n. So this thing is equal to 0. Then check. So by 1 and 2, we conclude that summation of -1 to the n plus 1 over n, this is convergent, right? If you can check these two conditions, well, then you can conclude that the series, the alternating series, converge. That is the point of alternating series test. Alright, let's do part B. So part B, we have a sub n equal to 3n over 4n minus 1. Alright, let's see if we can use the alternating series test. Well, we can see clearly that we can see clearly that if you compute limit of a sub n, so you're gonna have limit of 3n over 4n minus 1, and this is 3 over 4. Wow, what does it mean? This is not equal to 0, so the condition number 2 gonna fail anyway. So condition 2 is always not true, right? Because you have something not equal to 0, but condition number 2 said that you need limit of an equal to 0. So what does it mean here? So it does mean that the alternating series does not work, so we cannot apply the alternating series here. So if you want to check the convergent or divergent pattern here, what can we do? So we already compute limit of a n, right? When n go to infinity, we already have that this is equal to 3 over 4, which is not equal to 0. Then it does imply that limit of negative 1 to the n times an. This thing gonna swap between 3 over 4 and negative 3 over 4, right? It's gonna be 3 over 4, negative 3 over 4. I mean, at the end, the pattern gonna be getting close to 3 over 4 and getting close to negative 3 over 4. So it means that the limit does not exist. Well, what can we conclude here? So because the limit of summation because the limit of negative 1 to the n times an does not exist, so we can conclude by the divergent test. Summation of negative 1 to the n times an diverge, right? Because this thing is not equal to 0, so it's diverge. So we have learned that if you compute the limit and limit is not equal to 0, then the series is divergent. Simple like that by the divergent test. Alright, we have one more example for this topic. So part C, we have summation of negative 1 to the n times log n over n. Alright, here we have an equal to log n over n. Alright, we need to verify two things. So number one is an decreasing. So we're gonna let fx to be log x over x and then try to differentiate and check if the derivative less than 0 or not. So differentiate one time, so I have low d high, right, minus high d low over low square. And after I simplify this thing, I have 1 minus log x over x squared. Well, on the bottom I have x squared. This is always positive. On the top I have 1 minus log x. This is always negative when x is bigger than 3, right? So, right, because when x is bigger than 3, log x gonna be bigger than 1. And that means the top thing here gonna be negative eventually. So it does mean that f prime x gonna be less than 0 when x is bigger than or equal to 3. So that means a sub n is decreasing, right? Because we define the function that is similar to a sub n and we check by using calculus that the first derivative less than 0. Alright, number 2, we need to check that limit of an where n go to infinity, this is equal to 0. Alright, that is limit of log n over n. Yeah, for sure you need to use the L'Hopital rule, so we need to compute this thing by using the L'Hopital rule. So I extend the domain and then I use the L'Hopital rule. right? This thing by L'Hopital rule, because I differentiate the top function, so I have 1 over x, differentiate x, I get 1. So after that, this thing go to 0, right? So at the end, I have this thing equal to 0. Yes, good. So by condition number 1 and condition number 2, the series summation -1 to the n times log n over n. This is convergent by the alternating series test. Alright, let's move to section 1.7. This is absolute and conditional convergence. So before we head to the definition of absolute and conditional convergence, let me give you the idea behind this thing. So let's consider two series. So first we have the series that I box in green here. So summation of -1 to the n plus 1 over n. And second, I have the series that I box in red here. This is -1 to the n plus 1 over n squared. Both of them are convergent series. By the alternating series test, right? Because by the alternating series test, we have that limit of a sub n equal to 0, and here it is clear that a sub n is decreasing. So we can conclude that both 1 and 2 are convergent. However, if you look at the summation of absolute an, so for the series number 1 that I box in green here, it's gonna be divergent, because if you take absolute value here for series number 1, so you're gonna get 1 over n, which is divergent by harmonic series, or p series with p equal to 1. And then if you take absolute value for the series number 2, now you get summation 1 over n squared. This is convergent by p series. So it means that if you know that the series is convergent, it is possible that your summation of absolute an converge, or it is possible that your summation absolute an diverge. So we're gonna give them different names. If summation an converge and summation of absolute an also converge, then we're gonna say that this series is absolute convergent or converge absolutely. Well, on the other hand, if you know that your summation an converge, but your summation of absolute an diverge, then we're gonna call that this series converge conditionally, or it is conditional convergent. So let's look at example 22 here. So we can see that the series here that I highlight in light blue now, so this series converge absolutely. Why is that? This is because, well, this series converge by alternating series test, because we know that limit a sub n equal to 0 and a sub n is decreasing. And also, if we take absolute value of this series, so we get p series, p equal to 2, so it's converge as well. So this is the case that we have absolute convergent. All right. And then for example 23, if I look at summation of negative 1 raised to the n plus 1 over n. This converge conditionally because, well, again, it is convergent by alternating series test, but now when you take absolute value, it is p series with p equal to 1. So this is divergent. So in this case, we call that it converge conditionally. So the question is, when we face the problem, how do we approach to check the absolute convergence and conditional convergence? So the idea is we are going to look at the summation of absolute an first. If the summation of absolute an converge, then it must be the case that summation of an converge, and this means the series is absolute convergent. Well, but if absolute summation of absolute an diverge, well, this is the hard case because we need to figure out that summation an is actually conditional convergent or divergent. So let's look at example together and hope that after you see example you will feel better. Alright, let's start by example 24. We want to check if the given series diverge or converge absolutely or converge conditionally. So from what I just said from the previous slide, so we say that if we face the question like this, what are we going to do? We are going to look at the summation of absolute value first. And this thing is just summation of 1 over square root n. Alright. However, this thing is summation of 1 over n to the 1/2. So this is divergent by p series, p equal to 1/2. Alright. So because the summation of absolute an is divergent, it could be two cases. It could be that summation of an is actually divergent, or it could be the case that summation an is conditionally convergent. That is the big picture. So we need to check that, well, the summation of an is actually divergent or conditionally convergent. So we're gonna check by using alternating series test. So condition number 1, we're gonna compute. So first of all, we're gonna just look at an equal to 1 over square root n. And then number 1, so we want to know that is an decreasing? Well, the answer is yes. It is obvious, right? Because, well, because 1 over n is decreasing, right? As you increase your n, the bottom is getting more heavy, and then that means 1 over square root n must be decreasing. Well, you good with condition number 1. So condition number 2, limit of a sub n. So this thing is limit of 1 over square root n, which is 0. So condition 2 works. So by the alternating series test, so this thing is convergent, and we know more because the absolute value of this thing, negative 1 to the n plus 1 over square root n, is divergent. So it is conditionally convergent. Sorry, it's conditional convergent. All right, next. Well, let's do question B. So now, again, we need to check summation of absolute -1 to the n plus 1 over square root n cube first. Well, this thing is summation of 1 over n to the 3 over 2. Well, but luckily, this thing is convergent, right? Because this is P series where P equal to 3 over 2. So this is bigger than 1. So that means the series is convergent when you have the case that the summation of absolute an is convergent. Well, you done. Then we conclude that well, the summation of just -1 to the n plus 1 over square root n cube, this is absolute convergent. Easy like that because, well, once you know that summation of absolute an is convergent, it's gonna force that summation of an is also convergent, and we call this thing absolute convergence, as you see on the previous slide here that I highlight in yellow. All right, next. Well, the last two examples for this chapter. So question C. Well, I'm gonna just take absolute value and then see what happened. So what I have here is I have summation of arctan n. All right, I forgot this thing. N start from 1 to infinity, right? And then over n cube. All right, how do we check the convergence of this series? So we have seen arctan before, and I told you that arctan is the hard one to figure out the convergent and divergent pattern. So we need to use the comparison test. So we're gonna start by this fact. So we know that arctan n is less than pi over 2, where n is bigger than or equal to 1, because the graph of arctan is like this. So it's always below pi over 2. So I'm gonna use this thing. And then after that, if I divided everything by n cube, I have that. And this is pi over 2 times 1 over n cube. Well, you can see that this series that I just cloud in green. So this thing is summation of, well, I mean, if I look at the summation of pi over 2 n cube, this thing is a convergent series because this is a P series, right? This is a P series with P equal to 3. Well, the series that I make a cloud in green here. So this is convergent. So it's gonna force that this series arctan n over n cube must be convergent too. So by the comparison test, well, summation of arctan n over n cube is convergent as well. And because this thing is convergent, so it's imply that, well, then the series negative 1 to the n arctan n over n cubed, this thing is absolute convergent, right? Because when you take absolute value, it is convergent, so it means the original series is absolute convergence. So for part D, let's look at what we have here. So we have, well, let's consider again the absolute value first. So we have summation of n over 2n plus 1, right? And this thing is divergent by the divergent test, right? Because if you compute limit of n over 2n plus 1 where n go to infinity, this thing gonna be limit of 1 over 2 plus 1 over n, which is 1/2 not equal to 0. So by the divergent test, we conclude that summation of n over 2n plus 1, this is divergent. So it could be the case that it is the original series is actually divergent, or it could be the case that it is conditionally convergent. So what we need is just we need to look at the original series. And again, once we look at the original series, we can see that if we let an to be negative 1 to the n times n over 2n plus 1, and then we compute limit. So this limit does not exist because the behavior of n over 2n plus 1 gonna be the one that approach 1/2, but you have negative 1 to the n too, so at infinity it's going to be oscillate between 1/2 and negative 1/2. So the limit is not unique, so the limit does not exist. Well, we conclude that by the divergent test, right? Because this limit does not exist, is not equal to 0, right? So by the divergent test, summation of negative 1 to the n or times n over 2n plus 1, this thing is actually divergent. Alright, and that's it's all for chapter 1.